Okay, we're in the section 4 of the notes. So we worked through 3 sections already. We're going to move forward. As we move forward, it's going to be one section at a time. You should also move forward through those sections. Of course, if you find some of these sections to be too trivial, you can just simply glance at it, maybe do a few problems, go to the next section. But at some point during the course, you're going to find something you don't understand, and that's where you need to spend a considerable amount of time in that section. The structure of this document is going to look the same each time you look at a section. For example, it'll be materials for exercise. Exercise is going to be numbered 1 through 139. So this is exercise 4. So this entire section is designed to get you through exercise 4. You'll get there. Before you do that, we do recommend you read the contents, and we do recommend that you do the examples and follow the examples. I present the examples in a video format for those students that need to see it done in a video format. My name is Ron Bannon. This is a draft version. It's a draft version of Webster Wells' Advanced Course in Algebra, and that goes back to 1904. If you need to reach out to me, my email address is Bannon, that's B as in boy, the @ symbol, NNON.US. And I'll try to help you, all right? Again, this document is not available, is not being made available to the public yet, hasn't been published yet, but the prison mathematics people, that's a project, those participants have it. So the prison mathematics project participants have that. What does that mean? Incarcerated individuals and their mentors and any administrators dealing with the program have access to it. So what I'm going to do is just, not read the document to you, but, emphasize that you should be reading the document, all right? Now, I realize some people say, I don't have the document, could you slow down? Not really, but this is the document. It basically talks about solving an equation. What kind of equation? Pretty simple equations, all right? But, Wells is kind of detailed in what he's talking about. Now, he may use terms that are no longer used in algebra, like, for example, transposing. We don't use that term anymore, all right? But it's not a big issue. You could use it. Technically speaking, it's fine. It's just simply been dropped. And the reason for that is certainly a lot of people study algebra, they really had no comprehension of really what was being accomplished. And I think transposing, although reasonable, it turned out to be unreasonable for a large number of people. They didn't understand. They thought it just meant moving things around. Yeah, it doesn't mean that. All right? So he goes through a lot of stuff. No, I'm not reading that to you. And no, you couldn't read this by me scrolling by it. So what I'm going to do is, I'm going to go to this example section. It's right over here. And this is a simple review. Now, when I say simple review, I mean that. It's a simple review. It's a kind of review that we would give our students in today's algebra classes, all right, about how to solve an equation. And it really kind of pertains to how to solve a linear equation. But the bottom line is, you may read that and say, I don't know how that could possibly relate to what Wells was doing. It's almost identical with the exception that I'm not using the word transpose. All right? So I go through some examples and I talk about the method that we'd like you to follow. So I'm just going to outline that for you, the essential rules of solving an equation. These are linear equations. Simplify both sides, get the variable term on one side by adding or subtracting the same variable expression to each side of the equation. All right, get the constant term on the other side, opposing side of the variable term, by adding and subtracting the constant term to each side of the equation. Divide both sides of the equation by the variable's term's numerical coefficient. Check your solution in the original equation. And again, they go through examples of that. I'm going to go through the examples that Wells emphasized, all right? So let me do that, and I'll, one step at a time. Again, let me repeat this. Wells talked about transposing. I'm going to be doing what's known as the technique that's taught nowadays, at least in most schools. They subtract x from both sides. What does that accomplish? That gets the variable on one side, and they would add 4 to both sides. What does that accomplish? Again, the constant term on the other side. Well, if you did that, you would get 6 equals 2x. Then what would you do? Divide both sides by the variable term's numerical coefficient. And what would you get over there? I'll write it over here. You would get 3 equals x. Now, that's really an inappropriate way to read it. You really should read it from the letter. And how should that be read? X equals 3. Now, the check part, I'll write that down for you. You look at the original and see if it's true. Who knows? Maybe it's false. Maybe I made a mistake. 3 plus 2 equals, 3 times 3 is 9. I got minus 4. 3 plus 2 is 5. and 9 minus 4 is 5. That worked beautifully, and that's a condition, x equals 3, that makes this a true statement. Right? Work is given to you. This is work and an answer. This is work. This is answer. And again, it also talks about substituting and yielding 5 equals 5 in the end. All right, let's go to the next one. Now, for some students, what transparent over here is just getting the LCD. All right? Now, I think the best way to get an LCD is by inspection, but you may say, no, I can't do it by inspection. I need a better way of doing it. Well, I'm just going to review at a very primitive level how you get an LCD. You write the multiples of 3 down. You write the multiples of 4 down. And you write the multiples of 6 down and the multiples of 8. There's other ways to do it. I'm saying the most primitive way to do it is find a common multiple. If you multiple of 3 down, 3, 6, 9, 12. And this goes on forever. I don't want to go on forever. How about the multiples of 4? That would be 4, 8, 12. Well, I found a common multiple. How about the multiple of 6? 12. So right now, the common multiple, the least common multiple between 3, 4, and 6 would be 12. Unfortunately for 8, that's not the case. So let me write it down now for that. What do you get? 8, 16. Well, let's take a look at 3. What would you get? 15. And then you'd get what next? 18, right? Well, that's not the case. Let's do 4. 4, 8, 12. Well, 16 would work, but unfortunately, I'm not getting 16 from the 3. How about for the 6? 18 would be the next one. Well, let me put this down. And again, this is not a good way of doing it. The next one would be 24. Well, let me keep marching forward. What do you get over there? I'm adding 3 on, 21, 24. How about this one? You'd get 20. I'm adding 4 on, and 24. 24 looks good. What do you get over here? 24. So the least common multiple between those denominators, which we call the LCD, would be 24. Now, it pains me to see students do it this way, but you know what? There's nothing wrong with that. All right, I get it. It's just painful to watch. I'm going to erase it. Today I was reading the New York Times, and they were talking about Germany's transformation. And, part of it's just a visual. What they do, they took a picture of a woman in a hijab. I guess that's what they're indicating for change. That's why they took the picture. But on the board was the same old, same old, same old. And she was teaching grade school kids how to get an LCD or an LCM. Now, they were using the German term for it. But the bottom line, whether it's German or not, I can look at their work, I can't read German, by the way, and know how they would do this as an algorithm. So let me write this over here. They would put the factored form of 3 down. That's 3, because 3 is a prime number. They'd put the factored form of 2 down. Now, the way she did it at the board, she wrote 4, then she wrote 2 times 2. Nothing wrong with that. I'll put 2 times 2. I'll put the number 6 down. That would be 2 times 3. Again, she was at the board. She put down 6. She would put down 2 times 3. Then the 8 goes down. And again, if she did 8 at the board, it would look like this. 2, 4, 2, 2. And look at a tree diagram. 2 times 2 times 2. Then, of course, very little work was done after that, but they'd write the German version of what's called an LCM of 3, 4, 6, 8. And they could look at this and write that down pretty quickly. I'll tell you why. It must contain those factors. What are those factors? Definitely contains a 2. Definitely contains a 3. Now, how many factors of 2 are necessary? Well, the 8 needs 3. So what some people tell you is, it's the maximum number of factors that occurs in any one of those factorizations. How about the 3? It occurs at most once in any one factorization. So if you did that, what would you get? You would get 2 cubed, which is 8. 8 times 3 is 24. I got to be honest with you, that's a lot of talking through that. And I'm going to say you really should be familiar with arithmetic and how to do that. All right? But I'm not saying you are. You might have to go back and review that. Let me erase this. And a lot of work to do that. And really, for some students, it's totally unnecessary. But I say for a lot of students, it is necessary. And why are they necessary? They're trying to simplify this thing by removing the fraction. And how they do that, they multiply both sides of the equation by the LCD, which is 24, or what some people call the LCM of the denominators. Well, let's do that. That's 24 times 2/3 of an x minus 24 times 5/4 equals 24 times 5/6 of an x minus 24 times 9/8. 3 goes into 3 once, and it goes into 24 8 times. So what would you get there? You would get 16x, because 8 times 2 is 16. Let's go to the next one, minus 4 goes into 4 once, it goes into 24 6 times. 6 times 5 is 30. 6 goes into 6 once, 24 4 times, 4 times 5 is 20. That's 20x. Minus 8 goes in 8 once, it goes into 24 3 times, 3 times 9 is 27. So for some people, that's considered a simplification. There's no fraction over there. Now what do they do? Well, one thing I would recommend to do is take 16x from both sides and add 27 to both sides. What would you get? Minus 3 equals 4x. Now what would you do? Divide both sides by the variable's numerical coefficient, which is 4. So what do you get? Again, a lot of people read it as minus 3/4 is equal to x. I'm not saying that's wrong, by the way, but we really should read it from the x. What's the x? Minus 3/4. I'm noticing that in my answer key, but again, I want to encourage you. I want to encourage you to check it, and this is the check part. Check. These are simple linear equations. Generally speaking, they'll be pretty easy to solve and pretty easy to check. All right, let's go to the next one. I'm looking at it. It looks pretty simple. And when I say that, there's nothing really that disturbs me in it. I'm going to subtract 3x from both sides. Students often ask me, do I need to write that down? Well, the answer is, I don't know if you need to write that down. I wouldn't write it down, but you know what? It can't hurt to write things down. Minus 1. No, I wouldn't do that, would I? I'd add 7. Now, someone says, why would you do that and not take 1 away? Well, I want to get x on one side and the constant on the other. So let's see if that accomplishes. What do you get? 2x equals 8. Then I divide both sides by 2. I'm not going to write that down, by the way. X equals 4. I don't know if I'm right. Let's take a look at that. 5 times 4, we're checking it here, is 20. 20 minus 7. 3 times 4 is 12. 12 plus 1. What's 20 minus 7? 13. What's 12 plus 1 is 13. Certainly true. What's the condition that made that true? X had to have been 4. Let's go to the answer key. You'll notice that they put an answer down there for you. All right, let's do the next one. Next one, I'm kind of looking at it. Maybe I'm not getting too good at the LCM yet. Maybe you're a little rusty on it. But let's go through that, and I'll kind of go through it quickly. I'll write the 6 down for you. I will erase it, though. That's 2 times 3. The 3 is just 3, right? Factored. The 5 is just 5. And the 4 is actually 2 times 2. So what's the LCD? I like to say LCD, by the way. It definitely has a 2. It definitely has a 3. And it definitely has a 5. The maximum number of times the factor 2 occurs in any one factorization is 2. The maximum number of times the factor 3 occurs in any one of those factorizations is 1. And the maximum times the factor 5 occurs in any one of those factorizations is also 1. So what did you get over here? 4 times 3 times 5. 4 times 3 is 12, and 12 times 5 is 60. So this is the LCD. And what I'm going to do is I'm going to erase that now. You should consider doing some of this stuff in your head. And again, Wells says that a lot. So the LCD is 60. So what do? They multiply both sides by 60. Whoops. And this is an equation, it's fair and equal treatment. You're multiplying both sides by 60. Well, I think I could probably do this without, doing too much work. 6 goes into 60 10 times, and 10 times 7 is 70x. Minus 3 goes into 60 20 times, and 20 times 5 is 100. Let's see, 5 goes into 60 12 times, and 12 times 3 is 36. 4 goes into 60 15 times, and 15 times 1 is 15. Now what would I do? Well, I'm going to write it down for you. I would subtract 36x from both sides. That means the x is on the left side now. And I'd add 100 to both sides. Now, if you add 100 to both sides, the constant will be on the right side. What would you get over there? Well, let's take a look at it. 34, x on the left side. And on the right side, what do you get? You get 85. All right? So, what I'm going to do now, I'm going to divide both sides by 34. Now, sometimes you write it down sometimes, but not always. And what would I get? I'd get x equals 85 over 34. I'm happy for you. It's definitely a right answer. I do want to claim that, maybe you could reduce it. And someone says, how would you know you could reduce that? Just give it a shot. Let's take a look. So 85, I'm going to do what that woman did in newspaper, tree diagram. 5, because I know 5 goes into 85. And 5 times what? We're looking at it, 17. And why is that? 17 times 5 is 50 and 35, which is 85. Let's write 34 down. Now, what about 34? It's even number, so 2 definitely goes into it. 2 times what? 2 times 17. So I'm going to say 17 is a factor of both top and bottom. 17 goes into 85 5 times, and it goes into 34 2 times. So although 85 34ths is 5 halves, I think I would much rather have someone say it's 5 halves. It makes more sense to me. Let's look at the answer key. And when I'm pointing out the answer key, I do see the 5 halves, but also see they put down 85 over 34. Now, why do I do that for the students that didn't see the 5 halves? But you really should be looking at the key, and you should be looking forward to the simplest possible answer. Although equivalent, in other words, I'm saying they're equal, it's a better looking answer. 5 halves looks better to me. It's more reasonable in its tone, all right? I would recommend you check it. I'm going to say a good way to check it at this stage over here, if you're tired, is to trust me. And I'm going to say that could be a mistake. You go back in the original problem, and what I mean by that, let me write that down for you. 7, 6 times 5 halves minus 5 thirds, I'm checking now, is equal to 3 fifths times 5 halves minus 1/4. All right, I'm just checking. My eraser, I want that equal sign there. All right, get my eraser out. Get my pen back, and let's see if we can do it. Jeez, this looks like it might be a tough one, right? 7 times 5, that's 35 twelfths. Minus, well, I get twelfths, don't I? That would be 20. 12. So let me tell you what I did. 4 times 3 is 12. 4 times 5 is 20. Let's do this. This would give me 3 halves, but I want quarters, right? So 3 halves, and quarters would be 6 quarters. Minus 1/4. Again, I'm just checking. And let's take a look at that. What's 35 minus 20? That's 15, isn't it? Twelfths. And what's 6 quarters minus 1/4? 5 quarters. Well, I'm going to reduce 15 over 12. I'm going to divide by 3, and we get 5 quarters. It works out beautiful. All right, let me get my eraser out. And again, we don't really need to see your checks. It's nice if you check, though. Okay, let me do the next one. Looks a little complicated, and someone says, where's the answer? Well, it's on the next page, but I'm not worried about that now. I'm worried about doing it. You should be worried about doing it. 5 times 3 is 15. Let's see, 5 times 4x is 20x minus 9x minus 12x squared. Let's keep going. This is 15 plus 11x. I'm simplifying, by the way, minus 12x squared. That's the left side simplified. Let's do the right side now. You get 62 minus, let's do the multiplication. 7 times 1 is 7. Then I get minus 28x. Then I get minus 3x. Then I get plus 12x squared. All right, let's keep going. 62 minus 7. Now, minus 28 minus 3 is minus 31x's. Plus 12x squared. Let's keep going. Yeah, it's a lot of work. I guarantee they're going to work out pretty nicely. And what do I say? I see 62 minus 5. And what's that going to give me? 55. And then what I get? Minus a minus 31 is plus 31. X minus 12x squared. All right, what I'm going to do, I'm going to add 12x squared to both sides. I am going to subtract 11x from both sides. And again, I'm trying to get the variable term on one side. And I'm going to subtract 55 from both sides. Now, certainly when I do that, what do I get? I get, let's see, I get minus 40 on the left side. And what do you get on the right side? Geez, it looks like you get 20, right? 20x. Divide both sides by 20. And yeah, maybe I'm getting a little bit quicker over here. I'm going to say x is minus 2. Now, I realize, again, that checking business really gets people creeped out. But it's really not bad to check it. At a minimum, though, what I'd recommend you do is look at the answer key, see if you can agree with that. And that's minus 2. All right? Boy, I guess I did work in this one already. I'm going to erase it, though. And the reason I'm going to erase it, I'm going to do the work again. I don't know, maybe someone on a prior day asked me to do that problem. I can't remember. Erases all business over here. Actually, I can remember, but the story's too long to tell. All right, let me see if I can do it. So I'm going to look at it, and the one I would recommend to do is that there's many ways to do the problem. It's not just one way that someone does it. What I'm going to recommend you do is multiply both sides by some power of 10 that gets rid of the decimal. And in this case over here, I'm kind of looking at it, and I'm saying I'd have to move it 1, 2, 3, 4, I think about 4 places. So I'd multiply, let me write this down for you. I'd multiply both sides by 10,000. The effect of multiplying by 10,000 actually just moves the decimal places 4 places to the right. So if I did that, what would I get over here? Let me see. 2, let me write this down for you. 2, then 3 more zeros. All right, let's do the next one. And what would you get over there? If you did that, 4 places to the right would be 10. Minus, if I did that, that would be 300. X, by the way. What would this give me 1130x. And this would give me minus 161. All right, move up a little bit. I'll be careful not to look at that key. And what do you get over there? 1700 x plus 10. And I wouldn't worry so much about making mistakes, by the way. Mistakes are really good to learn from. All right, what am I going to do now? I'm going to subtract 1130x. And I'm going to subtract 10 from both sides. And again, I'm not beyond making a mistake. I can't say it enough times to you. Oh boy, that's like a tough problem. Nah, it's not that tough. So what do you get on the other side? The right side, minus 171. That's not so bad. What do you get on the other side? Let's see. I guess you get 570, right? And if I were to do that, I would just simply divide both sides by 570 now. What would you get? X equals minus 171 over 570. By the way, I don't mind the answer, but it's not polite. Let me tell you why it's not polite. They spoke to you in decimal, but you didn't answer them in decimal. I don't mind, though. Certainly I can understand it. It's like in the English language, we mix it a lot with other foreign words. Like, for example, the word kowtow. I'm probably not saying it the way that someone who speaks Chinese would say it, but it's actually a Chinese word, but we use the word. All right? We use the word as our word. It's not our word. It's somebody else's word. But it's okay to do that. It's okay to mix language. All right? It makes our language richer. I think one thing nice about the English language, we just throw any word into it from any language we care to do, right? Like we'll start to speak French sometimes. Not complete, but it's not bad. Right? We can do that. What I'm going to claim, though, is I do want to steer towards the decimal answer. I want to speak their language. So I'm going to go through that with you. And some you might say, I don't like the way you're doing it. We're not saying you have to do it this way, but I'm going to do long division for you. I'm going to do 570. And I'm going to divide it into 171. Yes, I know it's a negative number, but I'm just doing my grade school arithmetic. I think you remember your teacher told you had a 0 over there, all right? Now, I'm going to say, what's that all about? It just makes it easy. It's an algorithm for division. It's long division. So I'm wondering what times 570. I know it doesn't go into 171, but now I'm looking at 1710. It's almost like I'm looking at 1710, but I'm not. But I think I'm looking at that. And it makes it easier for me to reason with this. So what's the number over there? I'm going to say maybe 3 would do that. Well, what's 3 times 0 is 0. 3 times 7 is 21. Most people have to carry. 3 times 5 is 15. And 15 plus 2 is 17. This worked out beautiful. And what do I now know? I know x is equal to minus 0.3. That's a better looking answer. So I want to point that's over here. All right? And there's two ways I've done the problem for you. Just the way I just did it now, the way I just did it. I also did it saying I don't mind decimals. If you don't mind decimals, I would recommend just living with them. Just like if you don't mind fractions, don't clear the fractions out. But it's not bad if you have to clear a fraction to clear a fraction. It's not bad if you have to clear a decimal to clear a decimal. Decimals are easier to clear. The reason is you're just moving the decimal point around, and it's powers of 10. All right? Ooh, we're done, which is good news. What does that mean? You're going to be going through some problems over here, and we're recommending that you do those problems the way you're comfortable doing those. We're hoping you have some comprehension, though, of what was done prior. In other words, the content and the examples, and try to follow somewhat what we're doing, all right? And certainly there's answers over here, and there is work, all right? There's problems, and I know some problems, we might say, look at these, they're really difficult problems. I don't think I can get through all those, and I'm going to say you can get all those. The only thing I want to mention to you just briefly, there is this website that we'd like you to go to if you have availability to the website. It's the SAGE website. You can download the application. What kind of application are we talking about? A computer algebra system. It's a CAS system. That's how we abbreviate it. And you could also do the interactive web-based. And you type in these commands when you install the software. And what do you notice? SAGE can solve simple problems. More importantly, though, it's not for us to solve simple problems. It's for us to learn how to use a computer so when we get to realistic problems, we know how to solve them using a computer. I really appreciate your attention. Again, if you have any questions, don't hesitate to reach out. Thank you so much for paying attention.